Since the dawn of human consciousness, we have looked up at the night sky and wondered, where did all of this come from? This question connects us to our ancestors and drives our curiosity today. Science calls it the Big Bang, a story of creation, light, and mystery. But is it the final answer? The Big Bang Theory tells us our universe began 13.8 billion years ago, an explosion of space itself, not in space. From a hot, dense beginning, the universe has expanded and cooled, leaving behind cosmic clues, the expansion of galaxies, ancient light, and the elements we see today. This is our grand cosmic story. The Big Bang Theory describes the universe's evolution from its first moments, but leaves us with deep mysteries. What caused the bang? Why is the universe so uniform and flat? To solve these puzzles, scientists proposed cosmic inflation, an explosive expansion in the universe's first instant. Yet, even inflation leaves the true beginning shrouded in mystery. What if the Big Bang was not the true beginning, but a transition in a much larger cosmic process? Some scientists now explore the idea that our universe erupted from a white hole, an object that violently pushes everything out. Perhaps our universe emerged from the other side of a black hole in an older universe. This mind-bending idea could rewrite our understanding of where we come from. For centuries, we thought the universe was eternal and unchanging. But astronomers like Edwin Hubble discovered galaxies rushing away from us, evidence that the universe is expanding. Like dots on an inflating balloon, every galaxy moves away from every other. Rewind time, and everything converges to a single spectacular beginning, the Big Bang. The universe began as a hot, dense sea of plasma, trapping light in a cosmic fog. When atoms finally formed, light was set free. This ancient glow, the cosmic microwave background, was discovered by accident in 1965, confirming the Big Bang. That faint afterglow is our baby picture of the universe, proof that the cosmos began in a fiery birth. In the first minutes, the universe forged its basic elements, mostly hydrogen and helium, in a brief intense burst called Big Bang nucleosynthesis. Observations of ancient stars and gas clouds match these predictions exactly. This cosmic recipe is a powerful, testable pillar supporting the Big Bang theory. The Big Bang explains the universe's grand structure, a cosmic web seeded by tiny quantum fluctuations in the earliest moments. Gravity amplified these seeds, forming galaxies and vast voids. The tapestry of the cosmos is a direct result of quantum ripples from the universe's birth. The Big Bang set the universe in motion from a state of perfect order, giving time its direction. As the cosmos expands and entropy increases, we experience the flow from past to future. Our sense of time's arrow is rooted in the universe's hot, ordered beginning. The Big Bang Theory weaves together evidence from every corner of science, forming the Lambda CDM model, the standard story of our universe. It explains our origins, but leaves the deepest questions unanswered. What came before, and what sparked the beginning? The standard model is a triumph, but at its edge, mystery remains. The Big Bang Theory describes the universe from its first moments, but cannot explain the true beginning, the singularity where physics breaks down. This missing first page is science's greatest puzzle, hinting at new physics beyond our current understanding. The quest to uncover what came before the bang is the next frontier in our cosmic story. The cosmic microwave background reveals a universe with nearly identical temperatures everywhere, an astonishing uniformity. Distant regions, separated by vast distances, somehow share the same temperature, despite never being in contact. It's a cosmic coincidence that challenges the standard Big Bang model and hints at a missing chapter in our universe's story. The universe's shape is a profound mystery. It could be closed, open, or perfectly flat, balanced on a razor's edge. Decades of measurements show our universe is almost perfectly flat. Like balancing a pencil on its tip, the tiniest imperfection would have changed everything. This extreme fine-tuning is called the flatness problem, a cosmic puzzle still unsolved. The Big Bang Theory predicts the early universe should have created magnetic monopoles, strange, heavy particles with only one magnetic pole. But we've never found a single one, despite decades of searching. It's like baking a cake that should be full of cherries, but finding none. This monopole problem is a major crack in the Big Bang model, demanding a new solution. In the 1980s, physicists proposed a bold idea: cosmic inflation. In a tiny fraction of a second, the universe expanded at unimaginable speed, stretching space itself. This solved the horizon, flatness, and monopole problems, explaining why the universe is so uniform, flat, and free of exotic relics. A brilliant patch for the Big Bang. Cosmic inflation explains why our universe is so vast, uniform, and flat. But what powered this incredible expansion? The theory requires a mysterious inflaton field with properties unlike anything in known physics. We've replaced one cosmic puzzle with another, and the true origin remains a mystery. At the heart of our universe's story lies the singularity, a point of infinite density where the laws of physics break down. It marks both the beginning, as in the Big Bang, and the end, as in a black hole. Here, our knowledge ends, and a new understanding of reality waits to be discovered. For physicists, infinity in an equation is a red flag, a sign our theories have reached their limits. Nature doesn't produce true infinities. We never observe infinite temperature or density. The singularity at the Big Bang or inside a black hole marks a cosmic dead end where our understanding breaks down. To move forward, we need a new theory that unites gravity and quantum physics beyond the singularity. Our physical theories are like languages. General relativity describes the vast universe, while quantum mechanics explains the tiny, uncertain world of particles. But at a singularity, both must apply, and they clash, breaking down into mathematical nonsense. The universe is telling us, we need a new language, a theory of quantum gravity. The universe began with a singularity, the Big Bang, a boundary to our past. Black holes contain another singularity, a boundary to the future. These two infinities, one at the beginning and one at the end, mirror each other. What if a black hole's end could spark a new universe's birth? Two sides of infinity, forever linked. To solve the singularity problem, we need quantum gravity, a theory describing gravity at the smallest scales, where spacetime becomes granular, not smooth. Loop quantum gravity predicts spacetime is made of quantum loops, replacing singularities with a bounce. The Big Bang and black holes become cosmic bounces, not infinite points, transforming our understanding of the universe. What if the universe didn't begin with a singularity, but with a quantum bounce? Instead of a single creation event, our cosmos could be part of an eternal cycle, universes born from the collapse of others. The Big Bounce model suggests no true beginning, just endless transformation and cosmic rebirth. Black holes are the ultimate cosmic monsters, regions so dense not even light escapes. But what if they have a secret twin? The same equations that predict black holes also allow for white holes, cosmic opposites that violently push matter out. Though never observed, white holes linger in theory, hinting at stranger cosmic secrets. Imagine a white hole, not a cosmic vacuum, but a fountain, matter, energy, and light gushing out in a spectacular eruption. Unlike black holes, white holes explode outward, a mystery with no clear cause. Could they be gateways connected to black holes where matter is reborn elsewhere in the universe? The puzzle continues. Black holes and white holes are opposites, defined by their event horizons. For black holes, nothing escapes once inside. Gravity pulls everything inward. White holes, in contrast, only allow things to exit. Nothing can enter. Black holes are cosmic traps. White holes are cosmic fortresses. This difference in entry and exit hints at a deep connection to the flow of time itself. White holes are a valid solution in general relativity, but they're incredibly unstable, like a house of cards, collapsing at the slightest touch. Even a single photon would destroy them, turning them into black holes. Our universe is filled with ancient light, so white holes are just mathematical ghosts, too fragile to survive reality. The arrow of time points forward, as the universe moves from order to disorder. Black holes follow this law, increasing entropy, but a white hole would run time backward, creating order from chaos, violating the second law of thermodynamics. For this reason, physicists believe white holes are not just unstable, but physically forbidden. For decades, white holes were dismissed as impossible, unstable, violating time, and with no way to form. But new quantum gravity theories suggest a black hole's collapse could rebound, transforming into a white hole. This quantum process bridges black holes and white holes, making them part of a cosmic life cycle, not just a dead end. Once just a mathematical curiosity, the white hole is now a serious, though speculative, contender in physics. The idea that black holes could transform into white holes challenges our assumptions about space, time, and creation. Perhaps our universe itself was born from such a cosmic event, a white hole erupting from a black hole in a previous universe. What if our universe didn't begin from nothing, but from a cosmic transformation, a white hole eruption, not a singularity? The white hole universe hypothesis suggests our cosmos is a chapter in an endless cycle, where black holes in one universe spark new beginnings in another. A story of eternal rebirth, not a single miraculous event. What if our universe was born from a white hole, emerging from a black hole in another, older universe? Imagine, a massive star collapses, forming a black hole. Inside, matter rebounds, creating a new bubble of space-time, our universe. Our cosmos could be the offspring of another, part of a vast cosmic family tree. The Big Bounce model suggests our universe didn't begin from a singularity, but from a rebound, a bounce after a previous collapse. Instead of infinite density, quantum gravity creates a repulsive force, causing expansion. The bounce provides a natural, self-contained explanation for our universe's origin and its remarkable smoothness. Imagine a black hole in one universe connecting to a white hole in another, linked by a wormhole, a tunnel through higher dimensions. Matter falls in, is transformed, and emerges as a hot, dense plasma, the seed of a new universe. It's a cosmic reset, a mind-bending journey through space, time, and possibility. The white hole universe hypothesis offers elegant solutions to the universe's biggest puzzles. It explains the uniformity and flatness of our cosmos, not as coincidences, but as natural outcomes of a cosmic bounce from a black hole in a parent universe. This model replaces mysterious fields with a tangible physical process, solving old problems in a beautiful, simple way. The traditional Big Bang theory implies that our universe sprang into existence everywhere at once, an infinite expanse born from a single moment. The white hole universe hypothesis, however, paints a different picture. It suggests that our universe may have been born from a single finite seed. The amount of matter and energy that formed the parent black hole would have been enormous, but not infinite. This means that our universe, at its birth, may have also been finite in size, emerging from a white hole with a specific radius, determined by the mass of its parent. This idea has fascinating implications for the shape and scale of our cosmos. If our universe was born from a single seed, it suggests that what we call our universe might only be one patch of a much larger reality. The explosive eruption of the white hole would have created a rapidly expanding bubble of space-time. We live inside this bubble. Beyond the edge of what we can see, beyond our cosmic horizon, there may be nothing. Or there may be other bubble universes, born from other black holes, existing alongside our own in a vast meta-cosmic ocean, a multiverse of possibilities. This perspective also changes how we view the information in our universe. The black hole information paradox asks what happens to the information of things that fall into a black hole. The white hole universe hypothesis offers a radical solution. The information is not destroyed. It is transferred. The information that defined the matter in the parent universe is passed through the wormhole and becomes encoded in the structure of our new universe. The laws and properties of our cosmos could be a complex echo of the information that was lost in its parent, a cosmic form of heredity. This notion that our entire vast cosmos could have originated from a single, relatively small seed is a humbling and profound thought. It means that the billions of galaxies, the trillions of stars, and everything we have ever known could be the magnificent blossoming of a single ancient event. It connects the largest structures we see in the sky to the quantum physics happening at the heart of a single collapsed star. Our grand universe, in all its complexity and beauty, could be the spectacular and intricate result of one black hole's final creative act. The white hole universe hypothesis ultimately leads us to a vision of the cosmos that is both ancient and profoundly optimistic. It replaces a story with a definite beginning and a likely end, the heat-death of an ever-expanding, cooling universe, with a picture of an eternal, cyclical, and living cosmos. Our universe is not a one-time event. It is a single iteration in a potentially infinite series of cosmic death and rebirth. The end of one universe provides the seed for the beginning of the next, a grand chain of creation that has no beginning and no end. This cyclical model suggests that the universe as a whole is a self-sustaining system. It does not need a moment of creation from outside itself. It is a cosmic engine that perpetually recycles itself. Black holes in one cycle become the seeds for the white holes that ignite the next. It is a process of cosmic reincarnation on the grandest scale imaginable. This vision resonates with some of the oldest philosophical and spiritual ideas in human history, which envision time not as a straight line, but as a great wheel, endlessly turning through ages of creation and destruction. This eternal cycle offers a different perspective on our own existence. We are not the inhabitants of a universe that is slowly dying. We are part of a cosmos that is constantly being reborn. The very matter that makes up our bodies and our world was forged in a previous cycle and will one day collapse to seed a future one. We are participants in a timeless, cosmic dance. This idea imbues the universe with a sense of vitality and purpose, not one imposed from the outside, but one that is inherent in its very structure, in the fundamental laws that govern collapse and rebirth. We are left with a story that is both scientifically plausible and deeply inspiring. The white hole universe hypothesis, while still speculative, opens a door to a new way of seeing our place in the cosmos. It suggests that the beginning was not the beginning, and the end may not be the end. It tells us that we are part of a grand, unfolding narrative that stretches across eons and across universes. Our quest to understand our origins has led us to this incredible possibility that we are the children of a black hole, living in a universe born from a white hole, and part of a cosmic story that may never, ever end. The idea of our universe being born from a white hole is beautiful, but faces a major challenge. White holes are incredibly fragile. Like a perfect soap bubble, even a single photon could cause a white hole to collapse instantly into a black hole. To save the white hole idea, we need a deeper theory, beyond classical physics, to explain how it could survive. The white hole hypothesis faces a major challenge, the arrow of time. Our universe moves from order to disorder, as seen in melting ice or burning stars, an increase in entropy. But a white hole would reverse this, creating order from chaos, defying the laws of thermodynamics. How could such a process ever occur? The idea that black holes could be gateways to new universes offers a tantalizing solution to the famous black hole information paradox. This paradox asks what happens to the unique information of all the matter that falls into a black hole. Quantum mechanics insists that information can never be truly destroyed, while general relativity suggests it is lost forever at the singularity. The white hole hypothesis solves this by proposing that the information is not lost, but is instead passed through to the new universe. However, this elegant solution gives rise to a new and equally perplexing problem. If the information from the parent universe is transferred to our own, where is it? Our universe began in a remarkably simple and uniform state, a hot, dense plasma described by only a few numbers, like its temperature and density. It does not seem to carry the complex imprint of all the stars, planets, and civilizations that may have existed in the parent universe. How can a vast and intricate amount of information from a mature cosmos be passed through a black hole, only to result in the pristine, simple starting conditions of our own Big Bang? The information seems to have vanished all over again. This new puzzle could be called the information transfer problem. It is the information paradox, reborn in a new cosmic context. The white hole must act as a kind of cosmic reset button, taking the complex, high-entropy information from its parent and transforming it into the simple, low-entropy state of a new beginning. But how this process would work is a complete mystery. The laws of quantum gravity would need to provide a mechanism for this incredible transformation. a way to launder the cosmic information and begin the story anew with a clean slate. Some theorists propose that the information from the parent universe is not lost, but is instead encoded in the fundamental laws and constants of our own universe. The specific values of the speed of light, the strength of gravity, or the mass of an electron might be the legacy of the cosmos that came before. In this view, the information isn't in the arrangement of matter, but in the very rules that govern our reality. This is a fascinating and profound idea, but it is currently beyond our ability to test, leaving the fate of cosmic information as one of the biggest hurdles for this new story of creation. The white hole hypothesis faces a scale problem. Our universe is vast, yet even the largest black holes are tiny by comparison. Some suggest our cosmos emerged from a small star-sized black hole, but this raises a new puzzle. How could so little matter create so much? Cosmic inflation may still be needed to explain our universe's size. Ultimately, every scientific hurdle and every unanswered question surrounding the white hole universe hypothesis leads us back to the same fundamental barrier. All of these ideas, the quantum bounce, the stabilization of a white hole, the transfer of information, and the connection between black holes and new universes, are built upon a theory that does not yet fully exist. They all depend on a complete and consistent theory of quantum gravity, the holy grail of modern physics, that would finally unite Einstein's general relativity with the strange rules of the quantum world. Without this final theory, our ideas about white hole cosmology remain speculative and incomplete. We are like explorers trying to map a new continent using only a few scattered and contradictory reports from previous travelers. Theories like loop quantum gravity and string theory offer promising glimpses and potential frameworks for what quantum gravity might look like. And it is from these glimpses that the white hole hypothesis has emerged. But they are not yet the final word. They are still works in progress, facing their own internal challenges and lacking any definitive experimental proof to guide them. A complete theory of quantum gravity would provide the language we need to tell this story properly. It would replace the infinities of the singularity with a clear description of the physics of the bounce. It would explain the precise mechanism by which a black hole's event horizon transforms into a white hole's. It would dictate the rules for how information is transferred or reset between universes. It would tell us whether white holes are stable or not, and under what conditions they can form. It would turn our profound speculations into testable predictions, allowing us to search for concrete evidence in the cosmos. This is the frontier of 21st century physics. The quest for a theory of quantum gravity is one of the most challenging and ambitious undertakings in the history of science. The white hole universe hypothesis is a powerful motivator for this quest, as it shows the incredible explanatory power that such a theory could unlock. It gives us a tantalizing glimpse of a new cosmic narrative, a story of an eternal, cyclical universe. But to know if that story is true, we must first build the theoretical tools and find the new physics needed to read its opening chapter. The white hole hypothesis offers a compelling narrative of cosmic inheritance, but it is not the only idea that seeks to look beyond the Big Bang's singularity. Another fascinating and deeply strange possibility emerges from the very heart of quantum mechanics. This is the idea that our universe could have spontaneously appeared from literally nothing. Not just empty space, but the absolute absence of space, time, matter, and energy. This concept, known as a quantum fluctuation, challenges our most basic intuitions about cause and effect, suggesting a universe that is the ultimate free lunch. According to quantum field theory, nothing is not truly nothing. Even a perfect vacuum, stripped of all matter and radiation, is a seething, dynamic place. It is a quantum foam, where pairs of virtual particles and antiparticles constantly pop into existence and then annihilate each other in fleeting moments, borrowing energy from the void itself. This is not just a theory. Its effects have been measured in laboratories. This quantum weirdness suggests that the laws of physics allow for something to spontaneously arise from a state of non-existence, as long as it returns to that state quickly enough. But what if a quantum fluctuation was so large and energetic that it did not immediately disappear? Some physicists, like Alan Guth and Alexander Vilenkin, have proposed that our entire universe could be the result of one such fluctuation. In this scenario, a tiny bubble of energy and warped space-time could have spontaneously appeared from the quantum foam of a pre-existing void. This bubble, containing the seeds of a universe, would then have been instantly gripped by the process of cosmic inflation, expanding exponentially to become the vast structured cosmos we inhabit today. It is a story of creation not from a bounce, but from a random hiccup in nothingness. This idea is both terrifying and liberating. It suggests that the existence of our universe required no supernatural cause, no parent universe, and no prior state. It could simply have happened, a random but permissible event according to the fundamental laws of quantum physics. The total energy of our universe is thought to be very close to zero, with the positive energy of matter and radiation perfectly balanced by the negative energy of gravity. This zero total energy state makes it much easier, in a quantum sense, for a universe like ours to pop into existence from nothing without violating the conservation of energy. Another powerful alternative to a singular beginning is the idea of a cyclical universe, a cosmos that goes through infinite rounds of expansion and contraction. This vision, similar in spirit to the white hole model, but with a different mechanism, suggests that the Big Bang was not a beginning, but a big bounce. In this scenario, our universe is just the current phase of an eternal cycle. It began with a bounce, is currently expanding, but will one day reach a maximum size. At that point, gravity will overcome the expansion, and the universe will begin to contract, heading towards a big crunch. This contracting phase would be the mirror image of our expansion. Galaxies would rush back together, the temperature would rise, and the entire cosmos would collapse back towards a single, ultra-dense state. But just as in the white hole model, this collapse would not end in a singularity. Instead, when the universe shrinks to a microscopic quantum scale, a new physical force would push back, halting the contraction and causing it to rebound in a new, fiery Big Bang. This would initiate the next cycle of expansion, creating a new universe from the ashes of the old one, in a process that repeats for all eternity. This cyclical model, championed by physicists like Paul Steinhardt and Neil Turok, has a deep philosophical appeal. It presents a universe that is eternal and self-sustaining, with no need for a beginning or an end. It elegantly resolves the what came before question by answering the previous cycle. The initial conditions for our universe, such as its smoothness and flatness, are not lucky accidents, but are naturally set by the long, slow contracting phase of the previous cosmic era. The universe effectively smooths itself out before each bounce, preparing the stage for its next performance. While early versions of this idea faced challenges in explaining how the universe could survive multiple cycles without entropy building up to unmanageable levels, newer models have proposed mechanisms to reset the cosmic clock. These theories suggest that the bounce itself is a violent, cleansing event that reestablishes a low-entropy state, allowing each new cycle to begin fresh. The Great Bounce remains a compelling competitor to inflation, offering a different narrative for our origins, one grounded in a timeless, oscillating reality, where our Big Bang was just one of countless cosmic heartbeats. What if the Big Bang was a moment of perfect symmetry, creating not one universe, but two? This is the mind-bending idea behind the mirror universe hypothesis. Proposed by physicists like Julian Barbour, this theory suggests that the Big Bang was not the beginning of time itself, but rather a central point from which time flows in two opposite directions. At the moment of the Big Bang, two universes were created, springing back to back from a common origin. One is our universe, where time flows forward from that point. The other is a mirror image cosmos, where time flows backward. From our perspective, the mirror universe would be evolving from the Big Bang into its past. But for any observer in that universe, time would feel perfectly normal. They would experience their own past, present, and future, and their arrow of time would be pointing away from the Big Bang, just like ours. The two universes would be like two rivers flowing away from a single mountain spring in opposite directions. They would be causally disconnected, unable to ever see or interact with each other, but forever linked by their shared origin moment, a true Janus point looking into two temporal futures. This idea is, deeply rooted in the fundamental laws of physics, which are, for the most part, time-symmetric. The equations that govern gravity and electromagnetism work just as well if you run the clock backward. The arrow of time we experience is almost exclusively a consequence of thermodynamics, the fact that our universe started in a highly ordered state. The mirror universe hypothesis suggests this ordered state was the Big Bang itself, and that disorder increases in both directions away from it. This provides a natural and elegant explanation for the arrow of time in both universes without needing to assume a special, unexplained beginning. This concept offers a radical new perspective on our cosmic story. It implies that our universe is only half of the complete picture. On the other side of our beginning is another, equally vast and complex cosmos, a twin that we can never know. This theory avoids a singular beginning by reframing it as a symmetrical midpoint in a larger, timeless reality. It suggests that the answer to what came before the Big Bang is another universe, one whose future is our past. It is a profound and poetic vision of a cosmos born in perfect, balanced duality. Perhaps the most radical and mind-altering idea about our universe's origin comes from a concept known as the holographic principle. This principle, which emerged from the study of black holes and string theory, suggests that our familiar three-dimensional universe might be nothing more than a projection, a hologram. The real action, the true reality, would be taking place on a distant, two-dimensional surface that surrounds our cosmos. Everything we see and experience, stars, galaxies, ourselves, could be the holographic image of information encoded on this boundary surface. This idea sounds like science fiction, but it is grounded in serious physics. It arose from attempts to solve the black hole information paradox. Physicists Jacob Bekenstein and Stephen Hawking discovered that the amount of information a black hole can hold is proportional not to its three-dimensional volume, but to the two-dimensional area of its event horizon. This was a shocking clue, suggesting that three-dimensional reality might be fundamentally encoded in two dimensions. The holographic principle extends this idea to the entire universe, proposing that our entire cosmos is a projection from a distant two-dimensional screen. In this context, the Big Bang would not be an explosion in space, but the moment the holographic projection was turned on. The origin story of our universe would be rewritten as a story about the information on this distant surface. The laws of physics as we know them would be a consequence of the rules governing this two-dimensional information. The question of our beginning is thus transformed. Instead of asking what caused the three-dimensional Big Bang, we must ask what created the two-dimensional information field that projects our reality. It pushes the mystery of creation to another level of existence. While it is, honestly, pretty difficult to imagine how to test such a profound idea, some physicists are looking for clues. They are searching for evidence of the pixels of this holographic projection, a fundamental graininess in the fabric of spacetime that might be detectable with incredibly sensitive instruments. The holographic principle remains one of the most speculative and challenging ideas in all of science, but it offers a revolutionary perspective. It suggests that our universe is not the fundamental reality, but a beautiful and complex illusion, a cosmic hologram projected from a reality we can barely begin to comprehend. All of these alternative origin stories, the quantum fluctuation, the great bounce, the mirror universe, and the holographic principle, point toward a single, overarching theme. They all suggest that our universe may not be the only one. They are all, in their own way, gateways to the concept of a multiverse. This is the idea that our cosmos is just one bubble in a vast, perhaps infinite, ocean of other universes, each potentially with its own laws of physics, its own history, and its own unique story. The Big Bang was not the beginning of everything, but simply the beginning of our thing. The theory of cosmic inflation, which we use to explain our own universe's properties, almost inevitably leads to a multiverse. According to the theory, the inflaton field that drove our universe's initial expansion may never fully stop. While it decayed in our region of space to create our universe, it could still be driving exponential expansion in other regions, constantly spawning new bubble universes in an endless process called eternal inflation. In this scenario, new universes are being born every moment, like bubbles forming in a pot of boiling water, each one a separate cosmos, isolated from the others. The multiverse concept offers a powerful, though controversial way to address some of the deepest cosmic puzzles. For example, the fine-tuning problem, why the constants of nature in our universe seem so perfectly set to allow for life can be explained by simple statistics. If there are infinite universes, each with random physical laws, it is no longer a surprise that we find ourselves in one of the rare universes where the conditions are just right. We exist here because we couldn't exist anywhere else. It's not luck, it's a selection effect. These ideas take us to the absolute edge of scientific inquiry, blurring the line between physics and philosophy. We currently have no way to directly observe these other universes or to test these multiverse theories definitively. And yet, they emerge as logical consequences of our best attempts to understand our own cosmic origins. They show us that the story of the beginning may be far grander and more complex than we ever imagined. Our universe may be a single note in an infinite cosmic symphony, a single chapter in a book of endless stories. Theories of white holes, bouncing universes, and multiverses stretch our imagination, but science demands evidence. Astronomers worldwide are searching for faint signals, subtle patterns in ancient light, gentle shivers of space-time, and cosmic flashes that could reveal a different beginning. This is the frontier of cosmic archaeology, digging for truth in the light from the edge of time. Gravitational waves are ripples in space-time created by cosmic events like black hole collisions or the Big Bang. They travel across the universe, carrying information from the earliest moments. Detecting their faint background could reveal if our universe began with a bounce, not a singularity, offering a glimpse into a time before the Big Bang. While gravitational waves offer a way to probe the Big Bang itself, the white hole hypothesis makes another, more immediate prediction we might be able to test. If black holes can, over immense timescales, undergo a quantum bounce and explode as white holes, then perhaps this process is still happening today. The universe is filled with black holes of all sizes. Primordial black holes, hypothetical black holes that could have formed in the chaotic aftermath of the Big Bang would be particularly interesting. These smaller black holes would have a much shorter lifespan and would be the first to start exploding. If this theory is correct, then we should occasionally see a mysterious, powerful flash of energy from a seemingly empty point in space. This would be the signature of a small, ancient black hole finally reaching the end of its life and erupting as a white hole. This explosion would release a burst of high-energy particles and radiation, like gamma rays or fast radio bursts. These flashes would have a very specific energy signature, one that could be calculated from the theory. It would be a unique fingerprint that distinguishes it from other known astronomical events, like a supernova or a magnetar flare. This is a prediction that astronomers can actively search for right now. We have telescopes that constantly scan the sky, looking for transient events, for things that go bump in the night. Scientists can sift through the data from these surveys, looking for unexplained flashes that match the predicted signature of an exploding primordial black hole. So far, no definitive candidate has been found, but the search has only just begun. The universe is a very large place, and these events might be incredibly rare. But finding just one would change everything. It would be the first direct observation of a white hole. This search connects some of the most abstract ideas in theoretical physics with concrete observational astronomy. It takes the esoteric concept of a quantum bounce and turns it into a testable hypothesis. Look for a specific kind of explosion. A discovery would not only confirm the existence of white holes, but would also provide powerful evidence for the underlying theory of quantum gravity that predicts them. It would be a beacon of light from the quantum realm, illuminating the connection between the death of a black hole and the creative fire of a white hole, and giving us confidence that our own universe may have started in a similar flash. The cosmic microwave background, or CMB, is our baby picture of the universe, a snapshot of the cosmos when it was just 380,000 years old. It is a treasure trove of information, and its patterns hold clues not only about the universe's infancy, but also about what might have come before. While the CMB is remarkably uniform, it is not perfect. It has tiny temperature fluctuations, the seeds of all cosmic structure. The standard inflationary model makes very precise predictions about the statistical nature of these fluctuations. If our universe had a more violent or complex past, it might have left subtle scars on this ancient light. Theories involving a big bounce or a collision with another universe in a multiverse scenario could leave such a mark. For example, the collapse of a previous universe might not have been perfectly smooth. Some large-scale structures from that previous eon could have survived the bounce, leaving a faint, non-random pattern imprinted on our CMB. Scientists are meticulously scanning maps of the CMB for such anomalies. Strange cold spots, unusual alignments, or subtle patterns of polarization that do not fit the standard inflationary picture. These would be like fossils from a pre-Big Bang era, preserved in the universe's first light. One such tantalizing, though highly debated, anomaly is the CMB cold spot, a region of the sky that is unusually large and cold compared to the predictions of the standard model. Some have speculated that this could be the bruise left over from a collision between our bubble universe and another in the multiverse. Other theories propose that it could be a remnant from a pre-bounce era. While more conventional explanations, or even a simple statistical fluke, are more likely, these anomalies keep the door open for new physics and encourage scientists to keep looking for more definitive evidence. Furthermore, the white hole hypothesis itself might leave a subtle signature. If our universe was born from a single, finite white hole, this could imply a specific kind of curvature on the largest possible scales, or a unique pattern in the distribution of matter that might only become apparent in future, more precise cosmic surveys. The search for these subtle deviations is a painstaking process, requiring ever more sensitive telescopes and sophisticated statistical analysis. But it is a crucial part of our quest. The CMB is our oldest and most precious artifact, and it may yet hold the secret to a time before time began. The search for our true cosmic origin story is just beginning. We are entering a golden age of cosmology, with a new generation of powerful telescopes and experiments poised to revolutionize our view of the universe. These future observatories, both on the ground and in space, will map the cosmos with unprecedented precision, opening up new windows to search for the clues that could rewrite our history. The quest to understand our beginning is driving technology and theory forward, pushing humanity to new heights of discovery. We are becoming true cosmic archaeologists, equipped with the tools to dig deeper than ever before. Future gravitational wave observatories, like the space-based LISA mission, will be sensitive enough to search for the primordial background of space-time ripples with incredible accuracy. They will be able to distinguish between the predictions of inflation and those of bounce cosmologies, potentially giving us our first direct glimpse of the moment of creation. These missions will listen for the faintest sounds from the universe's birth, providing a definitive test for many of these alternative origin stories. The next few decades could be the time when we finally hear the echo of the bounce. At the same time, next-generation optical and radio telescopes will map the distribution of galaxies and dark matter on immense scales. Surveys like the Vera C. Rubin Observatory and the Square Kilometer Array will create the largest and most detailed three-dimensional maps of the universe ever made. These maps will allow us to test the predictions of different origin models with exquisite statistical power, searching for subtle patterns, non-random features, or evidence of large-scale cosmic anomalies. They will also be our best tools for hunting for the transient flashes of exploding primordial black holes, the potential smoking gun for white holes. This is a journey fueled by one of our most fundamental human traits, curiosity. The question, where did we come from, is not just a scientific one. It is a question that gives meaning and context to our existence. The ideas of a white hole birth or a cyclical universe are currently on the fringes of science, but today's fringe is often tomorrow's textbook. The search for evidence is a long and patient one, and it may not yield answers in our lifetimes, but the quest itself is a noble one. It is the process of science at its best, imagining the impossible, and then building the tools to see if it just might be true. Our journey began with the Big Bang, tracing cosmic history through ancient light and the first elements. But the story led us to a singularity, a mystery where knowledge ends. Now, bold ideas like the white hole suggest our universe may be a link in an eternal cycle, pushing us to the very frontier of human understanding. The white hole universe hypothesis is a beautiful, speculative idea at the edge of our understanding. It weaves together mathematics and imagination, reframing black holes and the Big Bang as part of a unified cosmic story. Even unproven, such ideas inspire new questions, guide research, and remind us that science is a creative, human endeavor. Contemplating that our universe may be just one bubble in a vast multiverse offers a humbling perspective. Each discovery has shown us a cosmos far vaster and stranger than we imagined. We are not the center, but students of an endless, evolving universe, invited to look up in awe and wonder at the mystery of it all. Our journey has brought us to the edge of what is known, and we are left with more questions than answers. Is our universe a one-time event, or a single cycle in an eternal chain? Was our beginning a singular moment of creation, or the explosive rebound from a previous cosmos? Is the standard story the final word, or just the first chapter we have managed to read? These questions hang in the air, shimmering with possibility. They are the great, unanswered riddles of our time, and they ensure that the human quest for knowledge will continue for generations to come. The path forward is both clear and incredibly challenging. It requires us to build new instruments capable of peering deeper into space and further back in time. We must listen for the faint whispers of primordial gravitational waves, scan the skies for the fleeting flashes of exotic explosions, and search the oldest light for the subtle scars of a pre-Big Bang era. This is the patient, difficult work of cosmic archaeology, of sifting through the evidence to piece together a story that happened billions of years before we existed. It is a challenge that will push our technology and our intellect to their absolute limits. And yet, this quest is not just about technology or data. It is about the enduring power of human curiosity. It is about the part of us that is not satisfied with the world as it appears, but that constantly asks why and what if. This is the same spirit that led our ancestors to chart the stars, that drove Copernicus to rethink the heavens, and that inspired Einstein to reimagine space and time. It is our most precious inheritance, the engine of all discovery. As long as we continue to ask these fundamental questions, our journey of understanding will never truly be over. In the end, the universe does not owe us simple answers. Its greatest gift may be the mystery itself. The fact that we, a collection of atoms forged in the hearts of long-dead stars, can even begin to contemplate our own origins is the most wondrous thing of all. The search for where we came from is a story without a final page, a journey without a final destination, and that is a beautiful thing. For it means there will always be new frontiers to explore, new ideas to imagine, and a universe of wonder that is truly and gloriously without